Swayam Prabha. Digital India. Educated India.
Welcome back. So, today's lecture we will understand the 30-degree phase shift when we have a star delta transformer YD or Y delta also as it is shown. And as I had told you in the last class previous lecture that ANSI standard requires that HV side phase to neutral should lead the corresponding LV side phase to neutral by 30 degrees. Of course, one side is delta and therefore, there is no directly neutral. So, we have to sort of put a star, a virtual star inside the delta winding and then mark that centroid as N and then see what is the one side there is a physical neutral available, other side we have created a virtual neutral on our phasor diagram. Then we have to see that in between the two there is a 30-degree phase shift. And as I said this, if you follow this notation in a 3-phase power system, you will not have circulating currents, that is the main motivation for it. Otherwise, when you take a round robin trip, even though there may not be any load connected to the system and there may not be any power flow, if there are voltages are phase shifted when you go around the loop, then that will create a circulating current and the transmission lines, transformers are mostly having inductive impedances or reactances, very little usually resistances. So, the power factor will be close to 90 degree, but yet wires have resistances and so you will have I square R loss and circulating currents flowing in the system, which we want to avoid. So, I think this I had told you in the previous lecture that if you follow like for example, I have this 2-bus system and I keep lower side delta and high voltage side star, which is a natural thing to do, and I have a transmission line and I have another side, there are loads here and I have another generator let us say sitting here, and if it is also star to delta in the same way and this being HV side, this leads the corresponding star to neutral by 30 degrees. Everything leads an unloaded system. So, all the these generators are also I am taking as identical, I am building a symmetrical system. Transformers are also 3-phase transformers are also identical, and if I have not connected any load to this one, then in this situation when there is no load, the generator should be running under no load condition, then there should not be any current which should be flowing. And remember the return path, where does it get from? It gets from the grounds which we connect here. So, the it is not like there is no flow, current does not have a return path, current does have a return path. So, if there is no load and if HV convention is that HV side line to neutral leads the LV side line to neutral by 30 degrees, then this voltage being identical, 30-degree lead created here, 30-degree lead created here, these two voltages will be identical. So, difference of the voltage divided by the line impedance will be 0, because the difference of voltage is 0, and so no current will follow. If however, you mess up and do not do this identical 30-degree phase shift on this side and on this side, then even though the magnitude of these voltages are identical on the HV side, because there is a phase shift between them, a difference in the voltage exists, and almost 90 degrees or 89, 87 degrees like that lagging a current will be produced, and that will create I square R loss here, 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 and you will unnecessarily be under no load condition also creating a lossy system. So, hence this standardization basically takes care of the facts. See, system like for example, the transmission system in India, let us take for example. So, spread all over the country, we are having one AC grid, and every time how will we guarantee that there is no circulating current flowing in the system under no load? This is what, and actually in the system there will be always load, but we want to make sure that our connections are such that unnecessary system circulating currents are not flowing in the system under light load or no load condition, because everything else will be finally only superimposed on this no load condition to compute the actual currents. So, what will happen is, if you just follow this system, this thing, a person let us say in Shillong or something is doing a transformer connection, and somebody let us say is doing transformer connection in Chennai, and there are thousands of kilometers apart, and the grid is meshed interconnected system, and everybody is following this convention, then you are sure that there will not be any circulating currents in the system. So, this is the advantage of standardization. Now, let us try to see how this connection is enabled, how this is achieved. So, to that end, let me first take the case. First is, this is more natural case, that HV is star side, stars, I mean the star connection is on the HV side and the LV is the delta side. Why do I say that this is the natural thing? Because you get the line to line voltage is √3 times in the in a balanced system, √3 times phase to neutral value, and that advantage we get if we connect it in star. So, therefore, it is better to have HV side on the star and LV side on the delta. So, I am going to use capital A notation for HV side, and I write 3 transformers here. This is first primary winding of the first 3-phase transformer, primary winding of the second 3-phase transformer, primary winding of the third 3-phase transformer, and I connect them, this comes here and I ground them. So, I call this as A, I call this as B, this I call it as N. So, this is VAN, this is VBN, and this is VC2N. This is VC. Now, let us draw the other side of the transformers. And let us take this thing out here, this is small a. So, its natural convention is to use for higher value capital notation, lower value smaller notation, B and C. Now, let us interconnect this. So, the interconnection that I am going to do is I am just, let us do something very simple. Let us connect A to B, B to C. We are wanting to create a delta connection. Thick wires are used as interconnectors, and C to E. Okay. Now, let us say that the turns ratio of the transformer is n is to 1, and these are 3 identical transformers. So, therefore, I have n is to 1, n is to 1 and n is to 1. Okay. This I will prefer to use for VA, VB and VC. Okay. Now, what is this voltage therefore? I will now just write using black color, or I should use some other color. This voltage is capital VA by N. This voltage is capital VB by N. This voltage is capital VC by N. And let us put the dots. I have forgotten to put the dots here. The dots are compulsory while marking the transformer. Now, let us also mark the line current here. This is the line current from this IB and IC, and the line current here is capital IA, capital IB and capital IC. Now, let us first of all do the thing algebraically. So, let me start here the algebra. So, what is this terminal at? Potential VB. What is this terminal at? Potential VA. So, what is the difference here? VA minus VB, and actually you know that these two voltages being transformer, these are exactly in phase, and this is VA by N. So, therefore, you know that VA by N becomes equal to VA minus VB, correct? VA by N becomes equal to VA minus VB. Similarly, VB by N becomes VB minus VC. So, therefore, VB by N becomes VB minus VC, and the third thing should be quite obvious to you. VC by N becomes equal to VC. This connector brings the VA voltage here. So, VC minus VA. So, VC by N becomes equal to small VC minus small VA. So, there is a symmetry in the cyclic notation in your connections, and on this side it should be clear to you. Now, because the system is balanced, we know that VB is A square. I will do it geometrically later on. VB is A square times of VA, and what is A? A is 120 degrees rotation in the anti-clockwise direction, operator A, e to the power j root 3 by 5. J is, my j is under root of minus 1. What is VC? VC is A times of VA. Okay. So, now let's work on this equation VA by N is equal to VA minus VB, which is same as VA minus VB I am substituting as V square VA, which is same as 1 minus A square VA, or in other words capital VA becomes N times 1 minus A square times of VA. Now, what is, if this is 1, let me do the geometry on this side. If this is 1 angle 0, this is A and this is A square. So, A square. Slightly shorter. So, when I say minus A square, I draw this line equal and opposite, and then I want to do 1 minus A square. So, parallelogram law of identity, I have to add this and this is the minus A square. So, complete the parallelogram, and this becomes root 3, this becomes root 3 leading how much angle? So, this is 120 degrees, so this is 60 degrees, and these triangles are equilateral. So, therefore, this is 30 degrees. So, therefore, one angle, this is going to be root 3 N VA at an angle of plus 30 degrees. So, this basically means N is implicit here, N is implicit here. What it means is, because any voltage is always, if nothing is said about a terminal and I say this voltage, then what is the reference? It is with respect to neutral, which is again under ideal conditions at the ground potential, which is a balanced condition, it is also at the ground potential, which is at 0 value. So, therefore, we have come to the conclusion that HV side voltage leads the LV side voltage phase to neutral by 30 degrees, and effective turns ratio has become root 3, and the single phase transformer had a turns ratio of small n. Now, here this phase to neutral to this phase to neutral has become root 3 n. So, therefore, this has become equal, this can also be called as capital N angle plus 30 degree. If you want, you can also treat this as saying that this whole thing n capital N angle 30 degrees actually is a complex number. So, if you want, there is nothing wrong, it is technically very correct statement that now the turns ratio from primary to secondary has become effectively a complex number. Of course, I am not going to use that fact, I am going to keep this separate and this separate. And I am just pointing this to you because there are also phase shifting transformers where actually a complex phase shift angle is created to achieve some balancing in the power system, but that is not something right now that I am going to dive deep into. I do not think I am going to go deeper into that. But complex turns ratio is also possible, and this is one straightforward illustration of it. But this we usually, because we balance 30 degree shifts everywhere, they cancel out. So, we in this particular case we just say that the turns ratio is root 3 times of n, and keep this side separately as a rotation in the voltage operator. Now let's look at the current. Okay, let me draw first the picture of geometrically. Before doing the algebra for the this connection, let me do the VA, do this geometrically. VA, VC, this is VB. Okay. And while drawing the figure, just assume that turns ratio is any small one or something like that, so that I don't have so much of space here to alter the size of the length of the vectors. So this same voltage, so I'll duplicate it. This same voltage, I'm writing for this side, is going to be VAB on the secondary side. This one VAB. So I'll mark this as A and this as B. Imagine that the tip is already on the A side. If you want, I'll just draw, but books usually don't show this tip. Now let's take this voltage, duplicate, and what is this voltage? This voltage is B to C. So therefore, pick this fellow from here, take him parallelly, bring him here. This is B, this should be C. And put the tip VB minus VC, so the tip should be, VB is what is being measured with reference to VC, so the tip is on the, rather the tip, I mean the arrow is on the VB. And then take the third one, VC, and that is going to be VC minus VA. So I take this, I duplicate this, bring it here, and no, because my diagram is not symmetric, slight issue is there, I bring it here and put it here. Okay, so VC, VC minus VA. So now the line side connections, everything is clear. This is how it will be shown on the figure. Now you have to imagine if you want to think this also in terms of line to neutral, or in other words a equivalent star here, then you have to imagine a neutral which is at the centroid of this triangle, and then this is VR, this is VB, or in other words, what is VB? Yellow color, RYB convention, and this VC is going to be somewhere BC to N. And this angle, if you draw a if you draw a vertical line here, then this, okay, let me draw a black line or a very simple gray line. This line is parallel to this line, and because this is VA to capital N, this VA to N now is lagging by an angle of 30 degrees. So this is what we have achieved here. This is VA to N. Rotate it in the anti-clockwise direction by 30 degree in this direction, and then you get V capital A to N. So I have to just mark this as this. So you can do it both for voltage, you can do it both geometrically and algebraically. But for currents it is more easier to do it, much more easier to do it algebraically. So let me do the same for currents now. Let me work it out for currents, the line currents. So let's look at what is this IA. Maybe best thing is to take this picture and move it down. In fact, I can paste. Okay. So let's write IA, small a. I am looking at the current on this side. And what is that current? That current is, so now I will rub this and write everything for currents here. Okay. So though the arrow is right now being shown outside, actually understand that it is actually still being done as currents only. So this is turns ratio is N:1. So the voltage has come down by N times and the current has gone up by N times with respect to the primary winding current, and the primary winding current here is I capital A. So therefore this current is going to be NIA. Similarly, this current is going to be NIB, and this current is going to be NI of C. So NIA current comes here, and what goes away? This one, NIC. So you are actually having NIA coming here, and what is going out from here is NIC. And so what is IA? What is IA? The difference of this minus this comes here as IA. So therefore the IA becomes N times of IA, N times of IA minus IC. Okay. Now what is IB? If you want to emphasize phasors, sometimes I put arrows. I'll put this arrow here to emphasize that. Let's do it for IB now. So NIB reaches NIB reaches I'm sorry, yeah, NIB comes here slightly more, this thing, NIB is coming out here, but NIA goes out from here. So what goes here is N times of IB minus IA. That clear? NIA goes out, NIB comes in, the difference becomes this IB, so it's NIB minus NIA. And so you should get comfortable with writing these equations, you should practice it yourself. It's a pretty non-trivial exercise. Now let's do the, and practice makes perfect. So let's look at IC. NIC comes here, NIB goes out here, so the IC is this difference. So therefore NI capital C minus NI capital B. Now again I'll just illustrate with what is happening with one equation. This particular equation I will illustrate it. So what I get? Sorry, again we will use our knowledge of symmetry because we are dealing with balanced system. So I know that IC, let me bring this equation down, and I know that IC is going to be A times of IA. IC is in the diagram, always all phasors in the C phase are going to be, line current in IC is going to be A times the line current IA. So therefore I can write this as N into 1 minus A IA. So again the simple arithmetic. This also you should keep practicing, even if you are woken up in the deep of the night, deep sleep also, and you are asked to do this thing, you should be able to do it mechanically. That is the idea. So you take 1, you take A, you take minus of A, complete the parallelogram here, complete the parallelogram, and now this angle being 180, this is 120, you know this is 180, other side also 180, so this is 60 degrees, symmetry, so 30 degrees, and also by symmetry we know this is root 3 times, if this is 1 1, this is root 3. So now root 3 lagging by 30 degrees, in other words minus 30 degrees. So therefore this is root 3 n IA minus 30 degrees. So again you can see from here also you can infer that actually the magnitude of the turns ratio line to line currents wise, if you look at these two transformers and imagine identical star star or whatever connection, then effectively the turns ratio has become root 3 times of n. And what did I have for, so let me write this equation also here and move it down so I can compare the two equations side by side. Copy, paste. Okay, so now look at it. VA by VA is an angle where n is here root 3 times of small n, and IA capital, again I am writing, by small ia, which equation am I referring to? I am referring to this particular equation. So IA divided by this, so root 3 n whole of this has to be taken in on the denominator here. So I get 1 by root 3 n, or in other words I can write this as capital N and angle minus 30 degrees, or in other words I get 1 by n angle 30 degrees. So VA is n times this VA further rotated by 30 degrees, and IA is 1 by n IA again rotated by 30 degrees. So therefore, when you do VAIA, I am sorry, complex power calculation, VAIA star, then it is going to be, when you multiply this n cancels with this 30 degrees cancels with, because I am doing a star operation, so there is a star operation done here. When I do a star here, I have to do a star here. So 1 by n remains as it is. IA will become IA star, and this plus 30 degrees will become minus 30 degrees. So when I add it with this plus 30 degrees and minus 30 degrees, it will cancel. So therefore, I get this power balance, which is what I should have. Means I assumed symmetry, then once I said symmetry, I assumed 120 degrees. So I should at the end get this, which I have got, which says that, so no physics problem is there. The real power which is entering the primary is, so if you write this as PA plus JQA, and if you write this as P small a plus J small qa, you get that PA equal to small pa, QA equal to small qa. So everything has worked out, nowhere any inconsistency has been created. To just summarize the two equations before moving to the next connection. So one equation in this case was, copy this, paste here, and copy this, paste here. So this is same as times of this, just to keep a bit. Okay. So these are basically my governing equations in this interconnection, and you can see that here it comes as VA minus VB, Here also it doesn't come as, because A is to A here, here is A to B, so here also it should be A is to B. No, 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 no. Just watch carefully. This side comes as VCIA minus IC. So there is something more tricky, more asymmetry or different that goes on, you know. I'm just making you aware. There's nothing very significant about this particular thing, but subtleties we should sort of understand and capture. Now let us take another standard connection, because I said HV should lead LV by 30 degrees. Doesn't matter which side is delta, which side is star. So therefore now let us assume, though usually I don't come across this connection as I had said, but this also helps our education and completeness also. So I am going to say that HV is delta and LV is star. So first let me draw the star side, that is much more easy to draw. A, B, C, and thick thing taken for interconnection. The two grounded here. Okay. Now let's draw the other side. Okay, I have drawn the other side. Again, I would like this to be A. Let me pull the see, I'm drawing it deliberately so that while looking at this, and if you also do it along with me, you will learn this trick of how to draw this thing. Now what is my challenge? Okay, this is going to be capital A, this is going to be capital C, this is going to be capital D, and I have to do these interconnections here in such a way that, now see here, if I just follow identical interconnections as I did here, then the delta side will lag by 30 degrees. So if I do just this connection to here, this connection to here, and this connection to here, then this line to neutral would be 30 degrees lagging this, but this being my HV side and this being my LV side, like 220 kV and 33 kV or whatever, so the same interconnection cannot work. Okay, so what will work? Let us see. This is VA, VB and VC. This side again VA, VB and VC. This side is perfectly fine. Now there are two ways uh, of looking at this. Let us come to this diagram. Okay, so let us come to this particular diagram, and imagine that, see what is, okay, let me pick this here for my work. Let me copy it here and paste it here. Okay, now imagine first of all what is this angle here. This angle is exactly same as this angle, but this angle is 60 degree. It's an equilateral triangle, so this angle is 60 degrees. Okay, now I am sitting here at minus 30 degrees. Basically I am sitting here at minus 30 degrees, but this VAN, which is sitting here at minus 30 degrees, I want to rotate it here. Now in the new one, this is my old one, and make this plus 30 degrees. So I should be rotating how much? I should be rotating this triangle, this whole thing hinged at the neutral, I should be rotating it by 60 degrees. Is it not? I should be rotating this whole figure by 60 degrees. So if I rotate this by 60 degrees, then what will happen? This line which is at 60 degrees, if I rotate it by 60 degrees this anti-clockwise direction, this line will become the vertical line. So this line will become the vertical line, and then everything will turn out to be, this diagram will turn out to be perfect. So let me take this and rotate it by, except that these are now capital ABC, remember. This is capital A, capital B and capital C. So these are capital A, B, C. So now everything is, this is the way I want my interconnection happening on the other side. So if that is the case, VA, this voltage then, I made something, did I make a VAC? I'm sorry, when I rubbed it, I made this mistake. This is C and this is B. Just look at this here. Sorry for this. I took this and rotated like this, right? So the C came down, A came up, B came on the, C came down, A came, C and A came on the vertical line, B came on the horizontal. I'll get this back. This is what I have done here. C comes down, A comes at the top, too dark. A, C, B, and this. Yeah, better. C comes down, A comes up, and now this. So now look at this. See, this voltage is VA. Okay, this is N is to 1, this is N is to 1, this is N is to 1. Now this VA voltage on this side should be VA minus VC. Is it not? This voltage and this voltage, so I will for the time being get rid of these arrows also. So this voltage, I'm sorry, this VA is this VA minus VC. So I should take interconnector and VA, this is VA, this should be capital VC. So my interconnector will start from here and connect on VC. So this is going to be my VA minus VC. If you want, I'll put a more this thing also. Now what about VB? So VB is parallel to this line. So therefore VB is going to be VB minus VA, because these two are parallel. So it is VB minus VA. So therefore this side is VB, and see, this is not connected here. This is, I'm sorry. So I'm sorry, what am I doing? Patience. A little bit of patience is required. This topic is also tricky. Take the interconnector, which I usually choose with thickness of 4, and connect this interconnector to BA. Bit very clear. Don't want to miss out anything. And then let's finally come to VC. So this VC is parallel with which line here? VCB. So this side should be basically VB. So what I am going to do, oops. Ooh. This is normal wire, not interconnector. This I bring here, and now I use my interconnector with a thickness of 4. And where do I take it to? VB. And I close my interconnection here. So So, now we can write our equations. Now everything has been, most of the hard work has been completed. We can again get back to doing our algebra and verifying things that we did geometrically. So, I get, we look at this voltage capital VA, what is this side connected to capital VC. So, VA minus VC, this is VA minus VC is n times the VA, in other words divided by n is going to be VA. So, let us take this equation. I am not going to write the other two equations now, done it once, no point in doing it twice. So, let us work on this equation. So, the small VA is VA minus, now you know this VC should be written as A times capital VA by N, which is same as 1 minus A VA by N, which is same as what is 1 minus A? We have already worked it out here. So, the 1 minus A is root 3 at an angle of minus 30 degrees. 1 minus A is root 3 at an angle of minus 30 degrees. So, therefore, I can write this as root 3 at an angle of minus 30 degrees by N. So, in other words, VA is VA divided by N by root 3 at an angle of minus 30 degrees, or to close it, VA is equal to N by root 3, this is HV side, this is LV side, at an angle of 30 degrees. So, what do you come to the conclusion? In this case, the capital N, the phase to neutral on one side and the phase to neutral on the other side are, earlier it was root 3n, now it is n by root 3, and even now the current voltage on the HV side phase to neutral leads the voltage phase to neutral on the LV side by 30 degrees. Similarly, now let us just quickly do this for the currents, and so I have IA here, I have IB here, I have IC here, and now n times of n times dots I have not put on the transformer. All right, currents I will do it in the next class. Thank you. All right. So, we have to now, we have calculated now this thing that the HV side voltage leads the LV side line to neutral by 30 degrees as we wanted, and now because earlier we had a star delta HV LV. Now, we have delta star as HV LV. So, what came effective turns ratio as root 3 by n, here is now coming the other way round, the dual of it, n by root 3. So, that also point we have captured. Now, we should be able to see the same thing with currents also, just like in the previous example when we did the y to delta HVY and LV delta. So, same thing now we should be able to see in the in this connection also. So, we need to complete the current current transformation from for the balanced load from the LV to the HV. So, let us say that this is my let us say that this is my circuit right now. This should be IA. The balance sources are connected here, though I have not shown here. This is current entering here on this is IB, and this current is IC. Okay. So, I have to calculate now. I have to calculate IA, IB, and IC. And I am going to start from this side. Usually, I like the star side analysis. I many times start from star side, because in my mental pickup when I say balanced load, I imagine that there is a balanced Z connected here, and then this side analysis to me conceptually in my mind it looks easier. So, I start analysis from this side, and load side usually is easier also to pick up. So, I start from here and then I move towards this side. So, therefore, I will assume that I know IA, IB, IC, I mean from there. If that is the case, if I know IA, IB, IC, then if the current here in this winding is IA, the same, because same current is going to flow here, and I should put the dots, should not forget to put the transformer dots here. So, if the current is going out from this line current is IA, and the winding current is the transformer winding current is also IA. So, because the voltage becomes n times here, the transformer's turns ratio is n:1. So, therefore, this current is in this direction is going to be IA by n. Similarly, in this winding the current is going to be IB by n, and in this winding I have very limited space here, this current is going to be IC by n. Why? Because this winding current is IC. So, this winding current and this is demagnetizing. So, this magnetizing current has to be IC by n. This is the MMF balance principle of the ideal transformer. Now, let us write the equation for IA. Let us write this equation for IA. So, the IA is going to be equal to, I am sorry, IA by, I am going to apply KCL on this node here. What is happening? This current flowing out of this node is small I small a by n, and this current going out should be equal to the currents which are coming in. So, I capital A comes in, and this transformer winding current IB by n comes here. So, these two sum and go out from here. So, my equation is going to be that IA plus IB by n is equal to small I small a by n. In other words, IA is going to be equal to 1 by n of IA minus IB. But if the circuit is a balanced circuit which we are analyzing, then IB can be written as A square IA. So, therefore, this will become 1 minus A square IA. In other words, 1 minus a square by n times of I a. But if this is 1, this is a, this is a square 120 degrees, then this is minus a square 60 degrees. So, completing the parallelogram 1 minus a square is root 3 at an angle of 30 degrees. So, therefore, this thing and this analysis we have done earlier, I just repeat it because I do not remember it many times. So, this is the root 3 I a at an angle of 30 degrees by n, or in other words I a divided by n by root 3 at an angle of 30 degrees. So, now compare these two numbers, this is these two equations, this is capital I a and this is compare this to this. So, we see we see that the effective turns ratio both whether I work with voltages or currents is going to be n by root 3. That is why this is correct, a capital N is equal to n by root 3, and the A phase to neutral HV side, A phase to neutral HV side leads A phase to neutral LV side by 30 degrees, and similarly the HV side current also leads the line current on the LV side by 30 degrees. So, the phase shift of 30 degrees, what happens with voltage also same direction, same amount of shift 30 degrees also happens with current. Now, we have verified this for both sides, I mean not both sides, we have verified it for Y delta transformer, delta Y transformer following the ANSI standard that the HV side voltage should lead the LV side voltage, that always means phase to neutral by 30 degrees under balanced conditions. This we have now verified. The consequence of this is that when the current voltage also goes by 30 degrees, current also goes by 30 degrees in the same direction, then the power factor which is seen on this side and the power factor which is seen on the other side also remains the same. So, this covers these two important 30 degree phase shift concepts. We will take up some examples afterwards. Thank you.